Okay, so we're going to pick up where we left off last class. So we're looking at how we calculate the pH of a solution, a combination of acids and weak bases that we know are a buffer. So when we look at our titration curve, where it's flat is typically what we refer to as our buffer region. And so that's the area on our titration curve where our weak acid and its conjugate base, so that's what's created after the hydrogen, after the proton leaves, that's where those are approximately equal. And so this means when we think about it in terms of equilibrium, when we think about it in terms of Le Chatelier, as you add either acid or base, it's going to react with the opposite component to maintain the pH. So let's look at our first problem. So example 1 says, what is the pH of a buffer that is 0.12 molar in lactic acid, and then we're given the chemical formula, and 0.1 molar in sodium lactate, and we're given that chemical formula. For lactic acid, Ka is 1.4 times 10 to the negative fourth. So there's a couple of things that I want you to notice with this. First of all, we're told right from the beginning that this is a buffer. So we should be thinking, since we know it's a buffer and we're asking to calculate pH, we're going to use this Henderson-Hasselbalch equation. The other piece that stands out to me here is that our two components are related to each other. We've got our lactic acid and we've got our sodium lactate. So even if we weren't told that this is a buffer, the fact that our two components are related should kind of indicate, hey, we've got a buffer going on. So when we think about what's going on with these molecules, our lactic acid, which is our HC3H5O3, that's our weak acid. And it's going to dissociate in equilibrium with the proton and with the lactate ion. That's what we call that. And so we've got that. So that's our weak acid. That should be pretty familiar to us by now. Now, our sodium lactate, that's a salt. It's a sodium and an anion, so cation and an anion. Our sodium lactate looks like this. It's our NaC3H5O3. Now, like any other salt, you put it in solution, it dissolves, it's going to dissociate into Na+, our sodium ion, and C3H5O3-, which is our lactate ion. Notice here, we've got our lactate ion. So what we've created is we've created a solution that contains both the acid and the conjugate base. And the conjugate base, which is this piece, is coming from a source that's not coming from the acid. Okay, so that's where we're forcing a buffer because we've got the weak acid and its conjugate base. So that should tell us, hey, this is a buffer, apart from the fact that it flat out tells us this is a buffer. So we're going to use our Henderson-Hasselbalch equation. In order to use that equation, we need not Ka, we need pKa. As you can see down here, a little bit farther on the page, we have our equation marked for us. So we are going to convert Ka into pKa, just like protons, or H into pH. Anytime we put a P in front of it, it means that we're going to take the negative log. So we're going to do pKa is the negative logarithm of 1.4 times 10 to the negative fourth, which gets us a pKa of 3.85 when we plug that into our calculator. Check my number. Pretty sure it's right, but check it, make sure. Okay, so now that we have our pKa, our question is asking us to calculate what is, oh, that was pointless. What is the pH of this solution? Okay, so now here's where our Henderson-Hasselbalch equation comes in. So we've got pH is equal to the pKa, which we just calculated, so 3.85, plus the logarithm of the ratio of the concentration of our base to our acid. So where do these numbers come from? In your head, you might be thinking, oh my God, I need to calculate, I need to use an ICE table, I need to figure out what the concentration of my base is. But hey, guess what? We simplify it a little bit. We're gonna look right up here. Here's the concentration of our acid. Here's the concentration of our base. Because our base comes from a salt that's gonna completely dissociate. So our concentration of our sodium lactate is the same thing as our concentration of our base. We are going to assume that because the weak acid is it's weak, so that means it's not going to significantly dissociate, but also if we think about it in terms of Le Chatelier, there's already conjugate base present. The contribution of the conjugate base from the weak acid is going to be negligible. So that means in terms of our concentration of conjugate base, that one we're going to ignore. So our concentration of our base is going to be 0.10 because that's what it says in our problem. Our concentration of our acid is 0.12, and there we go. Now we just math, okay? So we plug it into our calculator, 0.1 divided by 0.12. We take the logarithm of that, we add 3.85, and we get a pH of 3.77. So go ahead and make sure that you plug that into your calculator, check my work, make sure that you get the same answer as me. As always, I think I'm right, but could not be right. Okay, so we are going to move on. That was a weak acid buffer. So we had a weak acid and then a salt using its conjugate base. Now, if we look at a weak base buffer, it's going to work in a lot of the same ways, but we're going to substitute in POH for pH and PKB for pKa. So the base analogs of pH and pKa, our ratio of base to acid stays the same. So that's our note right here. So that part doesn't change. And then depending on what the question is asking us for, we can use our pH is 14 minus POH as our conversion to figure out what our pH would be, because typically POH isn't what we're going to measure. Okay, so let's look at our example that we're going to use. So here we have a reaction equation, and I've got this CH3-2NH molecule reacting with some water, and it looks like one of my hydrogens from water goes over to this first molecule. So that makes this a weak base because it's gaining a hydrogen, and that makes this thing over here its conjugate acid. Okay, so again, when we read this problem, it says calculate the pH of a solution at 25 degrees Celsius. That is 0.1 molar of the CH3-2NH compound and 0.1 molar of CH3-2NH2Cl. Nowhere in here does it say a buffer, okay? So we don't have that clue in, but we do have a different clue. First of all, we have our reaction equation. So we know that this thing is a weak base. So there's a possibility for a buffer. And then we look at our other component. Our other component has this chlorine here. Okay, so this is the positively charged piece. That's our cation. Our chlorine here is our negatively charged piece. That's our anion. So here's our conjugate acid, but in its salt form. So it's the positive piece, the cation piece combined with an anion. So this right here tells us that we have a buffer. So I know I have a buffer. I'm being asked to calculate the pH. I know that I'm going to need the Henderson-Hasselbalch equation. I'm going to modify it because I've got PKB. Now, there are several different ways that you could go about doing this. You could convert KB into Ka and then use the typical Henderson-Hasselbalch. You could modify the equation using POH equals PKB. Whichever way you choose, you should get the same answer. I'm just going to go with modifying my equation. So I'm going to use my modified equation here where I've got my concentration, the logarithm of my concentration of my base to my acid, and I've got my PKB. So my PKB is going to be negative log of my KB, so 5.4 times 10 to the negative fourth, plus the logarithm of the ratio of my concentration of base to acid. Now, my concentration of weak base is 0.1. My concentration of weak acid, or the conjugate acid salt, is 0.1. So I plug those two things in. the logarithm of 1 is 0, so that means my POH is equal to my PKB. That works out kind of nicely. Okay, so I type it in my calculator. I've got negative log of 5.4 times 10 to the negative fourth, which is 3.27, plus the log of 0.1 divided by 0.1. So 0.1 divided by 0.1 is 1. Logarithm of that is 0, so plus 0. So my POH is 3.27. Now, don't forget to answer the question that's being asked. The question that's being asked is, what is the pH? So our pH is going to be 14 minus 3.27, which is 11.73. And there's our answer. So if we go to the next pages, what we're looking at here is what happens when we add things to a buffer system. So again, the whole point of a buffer system is that it can maintain its pH when you add other things to it. And so we've got some graphs here of looking at how like adding base and how adding acid might impact the pH of a system. And we can think about this qualitatively using Le Chatelier. So the idea that if we add a base, it's going to react with the conjugate acid. If we add an acid, it's going to react with the conjugate base to ultimately reestablish our equilibrium. We can also look at this mathematically, and we can use Henderson-Hasselbalch to do a comparison. So here we have an equation. We've got HC2H3OH and water in equilibrium with our hydronium ion and our acetate ion. So that we're looking at acetic acid and acetate here. If we use our Henderson-Hasselbalch, so again, we're looking at our two components. We're not necessarily, well, we are told that we have a buffer up here, but if we look at our two components, we've got here is our weak acid. Here is a salt that's made of the conjugate base. So that tells us that we've got a buffer here. So we can use our Henderson-Hasselbalch equation to look at what our starting pH is. So we've got our Ka, so we're just going to plug this in really quick. So we've got negative log of 1.8 times 10 to the negative fifth plus the log of 0.1 divided by 0.1. Again, those concentrations are coming from my problem. That gets us a starting pH of 4.76. Okay, so this is our starting pH. Now we're going to look at what happens when we add something. Okay, because that's the whole point of a buffer system, is that if you can add something, it's going to reestablish or essentially maintain its pH. So here's our first addition. We're going to add 0.1 moles of acid to this system. So if we think about what this is going to do, we're going to take our original conjugate base, because that's what acid is going to react with. Our acid is going to react with our conjugate base. We're going to add some acid here, and then it's going to create more of our original weak acid. Okay, so when we think about how this is going to happen stoichiometrically, we're starting with 0.1 moles here. So if we add 0.01 moles of acid, that's going to decrease our conjugate base to 0.09. It's going to increase our conjugate, or it's going to increase our weak acid to 0.11. So we're thinking about it kind of like an ice table, but just we're kind of skipping some steps here. So we're looking at, if we add some acid, that means we're going to use up some of our base. So our base is going to go down to 0.09. Our weak acid is going to go up to 0.11. So that's going to use up the hydrogen. So now let's plug it in and see what that does to our pH. So we'll throw this into our Henderson-Hasselbalch equation. Ka is still the same, so we're still going to do negative log of 1.8 times 10 to the negative fifth. And then we're going to plug in our new ratio, which is 0.09 divided by 0.11, because that's our new concentration of acid and base. Plug that in, and we get 4.67 as our new pH. So if we look at where we started up here at 4.76, and we're ending down here at 4.67. Not a huge change. Okay, for all intents and purposes, that pH has stayed essentially the same. We can look at it the same if we add some base. Okay, so here, if we, and I can't remember if this question is set up to add to where we were or to start from the beginning. Let's treat it as if we're starting from the beginning. Okay, so new situation. We've got the same buffer. We haven't added acid. This time we're going to add base. Well, our base is going to react with our weak acid. Okay, which our weak acid is starting at 0.1. We're going to add some hydroxide, and we're going to add specifically 0.01 moles of hydroxide. That is going to use up our hydrogen, it's going to form water, and we're going to get our conjugate base anion here, which our original concentration is 0.1. So kind of a baby ice table here. We're going to use up the base with some of our acid, so that means our acid is going to go down to 0.09. That means our conjugate base is going to go up to 0.11. Plug it into Henderson-Hasselbalch. Let's take a look and see what that does. So pH is negative log of 1.8 times 10 to the negative fifth plus log of my new ratio, which is 0.11 divided by 0.09. And we get a new pH of 4.85. Also, not a significant change. Our starting original pH was 4.76. It's gone up a little bit. And so this is where we're looking at it is resisting that pH. So we can think about it qualitatively using Le Chatelier as kind of our framework. We can also look at it mathematically using our Henderson-Hasselbalch equation. Again, the equation is on your equation sheet, so this is not something that you need memorized. You need to be able to recognize when you're going to use it. So in that situation where you have your weak acid or base and then a salt of its conjugate, or if it go ahead and tells you that you have a buffer. So there we have it. That's how we calculate things with buffers.